My name is Vicky Commissar, and I'm a PhD student in biomedical engineering with IBBME. This is my second year here, and I'm based out of the Toronto Rehab Institute under the supervision of Professor Jeff Fernie. So for my work is focused on what we're calling our mobility kit. So it's a system of pressure-fit poles and horizontal handrails that you can clip onto these poles, and you can install them in a home and an apartment without having to drill into your floors, your wall, or your ceiling. So it's a temporary solution for someone who, say, has had a stroke and needs a bit of extra support to get around, but is in a rental and can't just go around making changes to the home. We're developing this in collaboration with an industrial partner, and we're planning to launch it within the next few months. And on the side, we'll be starting studies on developing evidence base for recommending parameters such as height and where these should be placed within the home.
Hi, my name is Shams Qasim. I'm an engineering science student working with the I was working with the Autism Research Centre this summer on designing a social prosthesis app for children with the autism spectrum disorder. The autism spectrum disorder is associated with three main characteristics: reciprocal social interactions, communication, and stereotype behavior and restrictive interests. We focused on reciprocal social interactions. Essentially, I designed an Android application that would use speaker recognition technology to analyze how long a child with ASD is talking in a conversation. And based on that data, we will be able to prompt the child when to speak accordingly, and also to gather information for research about how long they're talking in a conversation and how many turns they're taking.
I'm Anna Graber. I belong to the Center for Research in Healthcare Engineering. My project is about deciding how many specialists to employ in a specific clinic under different assumptions. We used Markov decision processes and developed an algorithm that returns the number of required specialists based on different assumptions that usually are true in reality. So this is my poster.
Okay, I'm Peter Sabo, and this is my partner Vidya Menon. We're from the Space Robotics Group at the University of Toronto Institute for Aerospace Studies. And what we're working on is trying to recreate a robotic dragonfly. So we're looking at dragonflies in nature. U of T actually has some facilities about 40 kilometers north of the main campus that has access to real insects and real dragonflies that we've actually been observing and testing to see how they actually move. And we're trying to take that sort of inspiration to recreate the kinematics, which is how the wings move, to try to recreate the dynamics, which is how the forces and the torques that are created from that. So we're developing simulations that will tell us what the aerodynamics will be, as well as prototypes that will mimic the sort of motion that real dragonflies sort of create. What we want to do is we want to combine those two things together, which has been very, very rare in the field so far, of trying to take those two things and synchronize them together with a real prototype and the simulations matching them. So what we have here with our prototype is we have a very, very small and light frame, which is made of mainly carbon fiber. The wingtip to wingtip wingspan is around 6 centimeters. The whole thing weighs less than half of a gram. And what we want to do is we want to take these actuators, which are very, very small piezo ceramic actuators, which basically will deflect as you put a voltage across it, to drive these wings such that the wings will flap up and down. And so what we want to do is we want to recreate the motion of a real dragonfly and see if we can measure the same sort of lift and match it to our aerodynamic simulations.